Good morning. Today we are going to our next section, that is electron spin resonance. Electron spin resonance, it is a technique which used the spinning property of an electron which are in resonance. Okay, it is a technique which used the spinning property of an electron which are in a resonance condition. We know that molecules have atoms and it has nucleus. Nucleus has proton and neutron. Neutron is in neutral state and proton, it has positive charge. In effect, the nucleus has positively charged, and around the nucleus it has electrons. Okay, so electrons have the orbital motion and spin motion. That is, electrons revolve around the nucleus. In addition to revolve around the nucleus, it rotates about its own axis. That is the spin motion. Okay, when we know that when a charged body rotates, surely it will create magnetic field. So it behaves like a magnet. Now let us see how the spinning property help in ESR technique. Before going to detail into the section, we need to understand the basic behavior or basic idea behind the diamagnetic and paramagnetic behavior of an electron. For this, suppose consider a molecule that contains paired electron. Note the point, consider molecule contains paired electrons. Both are negatively charged. Both are paired electrons and have negatively charged. One is spin up and another is spin down. That is, one is in the clockwise direction and other is the anti-clockwise direction. These are generated by the two electrons. That is, it creates the magnetic field. One is in the upward direction and one is in the downward direction. That is, one is in the clockwise and another is in the it rotates in the anti-clockwise direction. If it rotates, if the electron rotates in the clockwise directions, it is spin up, and if the electron rotates in the anti-clockwise direction, the magnetic field is in the spin down, that is in the downward direction. Okay, this magnetic field generated by the electrons are antiparallel. That is, one is spin up, another is spin down. Obviously, there is the chance of the self-cancellation. Notice the term self-cancellation of the magnetic field generated by the two electrons. Why this self-cancellation occurs? Because it is paired electrons. Okay. Now, this rotation of electrons around the axis, we have used a term that is nothing but electron spin quantum number. That is the ms value. That may be plus half and minus half. If this self-cancellation occurs, we call it is the diamagnetic property. Okay, diamagnetic property. And now we take the another possibility, that is, if the molecule contains unpaired electrons and it may be the odd number of electrons, there is no chance of the self-cancellation of magnetic field created by these electrons. Okay, this paramagnetic, that is the paramagnetic behavior. This is the paramagnetic behavior. That is, there is no cancellation of the magnetic field. That is, there may be the net magnetic field. Iron, nickel, free radicals and electrons of triplet states, they are the examples of the paramagnetic. Suppose the paramagnetic behavior of this element, that is, the paramagnetic behavior of these elements is known as the term that is ferromagnetism. Okay. So, I think you got the idea what is diamagnetic and what is paramagnetic. For the diamagnetic, we take paired electrons So there is self-cancellation of the magnetic field created by the two electrons. In the case of the paramagnetic, it is unpaired electrons, that is odd number of electrons, so there is no chance of the self-cancellation. Okay, this in ESR, these paramagnetic electrons, only paramagnetic electrons that are taking part in ESR. That's why we call ESR, that is electron spin resonance, is also known as electron paramagnetic resonance. Okay, ESR is also known as EPR. Now we go to our principles of ESR. For this, just consider these points, that is the spin and charge of electron. It constitutes the spin magnetic moment, that is mu s is equal to minus g mu b s divided by h cut. S is the spin magnetic, mu s is the spin magnetic moment, and g is the gyromagnetic ratio, mu b is the Bohr magneton. Okay, if we express this in terms of the h cut, that is h cut equal to 1, if we consider h cut equal to 1, that is mu s is equal to minus g mu b s. If there is only the presence of the, or there is only the chances of the orbital magnetic moment, this mu l, now the equation changes to mu l equal to minus mu b l. That is, if there is orbital motion, there is no spin motion. So g is 1. So mu l equal to minus mu b l. So the total magnetic moment mu equal to mu s plus mu l, that is equal to minus g mu b s minus mu b l. Suppose if the system has only spin magnetic moment, that is if there is no orbital motion, that is the electron has only the spin motion, that is electrons revolve, electrons not revolve, electrons rotates about its own axis, that is it has only spin magnetic moment, then what happens? Mu is equal to minus g mu b s. This negative sign is that shows they are in the opposite direction, that is mu and s are in the opposite directions. Now what happens when we place an electron in the magnet having the magnetic field placed in the having the magnetic moment mu placed in the magnetic field B? What happens? There should be the possibility of the interaction energy between the electron spin and the magnetic field. In the case of the NMR spectroscopy, we treat nucleus, but in the case of the electron spectroscopy, we treat the electron, and all the theories are almost the same. So now let's watch. Okay, E is equal to minus mu dot B, that is minus mu B cos theta. Now we can replace this cos theta in terms of magnetic quantum number, that is ms, that is ms divided by s. We get E equal to g mu b b ms. Now we substitute the values for ms, that is plus half and minus half. That is, if there is the chances of electrons rotates in the clockwise direction and in the anti-clockwise directions. So the interaction energy changes to plus half g mu b b and minus half g mu b b. Now in the absence of the magnetic field, there is no splitting, and in the presence of the magnetic field, there is Siemens splitting, one for the ms equal to minus half, one for the ms equal to plus half. Now this energy is equal to interaction energy difference, that is the difference between these two energies, that is g mu b. When this energy, that is when this energy difference between these two energy levels, that is the energy gap, is equal to h nu, then only the transmission occurs. Okay, that is the resonance condition, that is h nu equal to g mu b. That is the resonance condition. Okay, for free electrons, G is equal to 2.0023 And now we consider the field is 0.34 Tesla. The resonance frequency nu is approximately equal to 9528 megahertz. This frequency falls in the range of microwave region. Hence, microwave source and techniques have to be applied for the observation of the ESR. That is microwave source. We need the microwave source for obtaining the ESR spectroscopy. Okay. I think you got the basic idea behind the ESR or APR and the principles of the ESR. Okay. In the next class, we will deal with the another topic. Okay. Thank you.